guys, welcome back to week 3 of my series where I'm learning ML through an organization perspective. This week I'm in the Boyd book, so I just finished on chapter 2.3 and completed all the exercises. I also reviewed last week's material and did some additional exercises, so I spent about 13 hours studying this week. So this week was a really good week, so I'm satisfied with the progress so far and how much I'm learning. I mean, progress is slow, but I find that ideas are very rewarding to learn about when I take them slowly. For example, I will talk later about perspective functions, but seeing how they work geometrically reminded me of optical physics, which is what I studied back in the day. So anyways, this week I learned about operations that preserve convexity of sets. So the basic idea is that given a convex set C, what can we do to C such that we preserve its convexity? So remember, a set is convex means that if we pick any 2 points in the set and draw a line segment between them, then the line segment must also be in the set. So this is important to ML because we do many operations on convex sets, but we need to understand what operations maintain convexity. So that's what I'm going to talk about today, some interesting operations that preserve convexity of convex sets. The first idea is simple. You take any 2 convex sets. So just to give an example of 2 convex sets on screen here. So you can see a convex set on the left, which is blue, and another one which is pink. So notice that they're convex, just visually speaking, because if you take any 2 points in the set, then the line segment that connects them must also be in the set. This is a property of circles and ellipses. And so if you sort of overlap them and then look at the set, which is the intersection denoted by this purple one here, then we can see that this set also must be convex because the 2 sets were convex and the intersection of 2 sets must be convex. So hopefully this makes intuitive sense, and the proof is also easy. Remember that an affine set can be thought of as a subspace plus an offset. Well, an affine function is a sum of linear functions and a constant, or has the form ax plus b, where A is a matrix and b is a vector. We can show that if x comes from a convex set, let's call it S, then the image of S under F is also convex. We can also show that the inverse image of S under F is also convex. So these 2 theorems have important implications, and I'm going to show you some examples. But before we do that, I'd like to show you just visually why an affine function preserves convexity. So pretend that we have an original set S, and then we apply the affine transform, and then we can see it's just a linear transform with some offset. And of course, intuitively it should make sense that this preserves convexity as well. We also have the Minkowski sum, which preserves convexity. So the Minkowski sum of 2 sets is simply just you do all the element additions for each element, and then you just add them all up and you get a new set. So on screen here is just 2 sets, set 1 which is blue and set 2 which is red, and then you take any 2 elements. So let's say I take element from here, take element from there, and you add those 2 vectors together and we get some result here. And so this result is then added to the sum of the sets. And you do that for all such pairwise elements of the blue set and the red set, and you get the Minkowski sum. So this Minkowski sum is also convex, assuming that S1 and S2 are convex as well. Also, the projection of a convex set is also convex. So for example, if we have a 3-dimensional convex set hovering above the xy plane. So in this case, the convex set is our blue sort of diamond here in 3 dimensions. And then what we do is we sort of project it down into the xy plane, which is where you see this orange box. And then once we project it down, our claim is that any projection into lower dimensional space will preserve convexity. And indeed, in this example, the square, which is the projection of this diamond, is also convex. finally, you can show that the partial sum of two convex sets, so in this case S1 and S2, is also convex. Note that when n equals 1, n equals 0, we have the Minkowski sum we talked about earlier. That's because when n equals 0, we don't have any x's available, and we simply just have y1 plus y2 for all y1 in S1 and y2 in S2, which remember is just the definition of the Minkowski sum.
I can't think.
So I'd like to go into more depth about what we call perspective functions. So I thought they were super hard to understand at first, but I thought they were so cool once I got to know them. So first I'll provide the definition of a perspective function. Have a moment to read it.
What am I supposed to do?
And the following result. If C is a subset of the domain of the perspective function P, then its image is convex. Okay, so what does any of this actually mean? Which is what I asked myself, and I'm sure that you're asking yourself the same question. Well, let's consider an example of literally perspective and how mathematically that works. So let's say that you have some object in the room, so R3. So it's just somewhere in the room, so it has coordinates x1, x2, and x3. So you orient yourself such that x3 is in the up direction, x1 is to the right, and x2 is in the depth or distance into the page. So let's say that there's some origin in this space, so at 0, 0. There we have some pinhole where light can get through. Now let's say that there's a horizontal wall at x3 equals -1. So the question is as follows. Where would the object show up on the horizontal wall in relation to x1, x2, and x3? Okay, so we already know the value of x3 is -1, and so we just need to find x2 and x1 for this image position. Well, we can use simple geometry as follows. Ignoring x2 for a moment, we can draw a triangle from the object to the pinhole as follows. And we can draw a triangle from the pinhole to the image location on the horizontal wall. The key idea is that these triangles are similar triangles, meaning that the ratio between x1 and x3 stays the same. So if x3 goes from 0 to -1, then to preserve the ratio, x1 must go from 0 to -x1 over x3. And the same idea remains for x2. So our final answer is here. So going back to our claim that perspective preserves convexity. So it says here that if C is a set that's a subset of the domain of P, so that has to be convex, then the image of that under the perspective function is also convex. So what that is really saying is that take all the possible values for our object, not just x1, x2, x3 in particular, but all possible values of x1, x2, and x3 that it can make up. So maybe the object can be somewhere here, and that sort of the possible locations must form a convex set. Then the resulting shape from all of those positions on the wall is also convex. So that's really what it's talking about. That's the perspective interpretation of this theorem. So I thought this is really, really cool. What's more is that the inverse image of a convex set under perspective is also convex. So this interpretation is that when you have a convex set on the horizontal wall here, then the resulting shape from the positions of the object which would have made that shape on the wall is also convex. So I thought that was pretty cool as well. Okay, so I know what you're thinking, so what? This is all pretty cool, but admittedly, this is pretty abstract stuff. Where's the application in machine learning? Well, I had some, same questions as you, and I did some searching. So here's 2 examples of what I found. Consider you're working in epidemiology, and you care about the incidence rate, aka R is equal to K over N, where K is the number of classes for each class, so it's a vector, and N is the population size. Notice the similarity with the perspective function. But because you're working with real data, you don't really know the exact vector K or the value N, but you do have some bounds for them. So this defines a set C of possible pairs of K and N. Thus, C is a convex set. Now, when you apply the perspective function to C, you get exactly your infection rate, which is K over N. And based on the theory above, you know that this set is also convex. I guess the deeper theoretical reason for so what is that it bridges the gap between conic optimization and classical geometry. We saw before that with infinite cones, like positive semi-definite cones, are easy to define and work with, usually speaking. However, bounded objects such as ellipsoids or circles or polyhedrons even are harder to work with or describe. So the perspective function allows us to describe the more complicated objects as literally a slice of the infinite cone. So, as in the left side, think of a flashlight cone where the center is the pinhole, and the horizontal wall is a slice where we see our object. If the wall is straight relative to the pinhole, we get the blue slice, which is the circle. And if it's tilted, we get an ellipsoid. So we can understand circles, ellipses, parabolas, and even hyperbolas in the general form just from studying a cone. Plus, since the cone is convex, every possible slice of that cone is also convex. Finally, I learned about linear fractional functions, which are compositions of the perspective function with an affine function. It turns out that these functions preserve convexity too, but I won't go into any more details in the interest of time. These linear fractional functions sort of generalize perspective functions and have many really cool applications in theory too, of course. So this week was honestly not that much math, but rather a lot of thinking. I mean, sometimes it was hard and sometimes very hard at times, but seeing all the stuff I just described to you felt very rewarding and cool. So I'm looking forward to continue learning. So I'll see you next week.